Okie dokie, folks. So you've already done a huge, massive, very fast crash course through atoms, matter, elements, the makeup of an atom, protons, neutrons, electrons, etc., etc. And hopefully you have all the materials you need. So even if right now you're a little bit confused, a little bit lost, you can refer to your vocabulary chart and the reading to kind of as you need, attain mastery in your own time. So right now we're going to move on to chemical bonding, okay? And anything in black letters in this PowerPoint, I want you to write down within your notes. So to review, elements in the same column of the periodic table have similar properties because they have the same number of valence electrons. And remember, valence electrons, this term refers to the number of electrons that an atom has within its outermost shell, okay, in the highest energy level. So across the periodic table, I've shown you in group 1 over here, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, they all have one valence electron. In group 2, they have 2 valence electrons. Are you guys starting to see a pattern? In group 3, boron, aluminum, and so on and so forth, they have 3 valence electrons. In group 4, they have 4 valence electrons. Okay, in group 5, 5 valence electrons. Group 6, 6 valence electrons. Group 7, 7 valence electrons. And group 8, called the noble gases, 8 valence electrons. And these over here, you might be wondering what's happening with them. They're semimetals. They have a variable number of valence electrons. In biology, we don't really care about them, okay? So, a Lewis symbol, I guess this is just sort of trying to remember what you guys have learned in your chemistry class previously. It's essentially just a little dot diagram that shows the number of valence electrons as dots around a chemical symbol. So for example, if I were to draw a Lewis dot diagram over here, okay, carbon has 4 valence electrons, so I would draw 1, 2, 3, and 4, okay? And sodium has 1 valence electron, so I would draw just 1 dot. Oxygen has 6, so 1, 2, 3, 4, 5, and 6. Okay, and you guys get the idea. So Lewis symbols of some group A elements over here. Group 1A, hydrogen, lithium, sodium, potassium, all have 1. 2A, all have 2. 3A, all have 3. 4A, all have 4. And so on and so forth. And you guys can refer back to the slide, pause at any point in time if you ever need to remember. Okay, I will draw your attention very specifically to 3 elements right here who I'm going to tell, or rather 4, okay, who I'm going to tell you right now, right here. You need to memorize how many valence electrons they have because it is crucial to biology. Number 1 is hydrogen. You need to memorize that hydrogen has 1 valence electron, okay, in its outermost shell. 2 is carbon. You guys might have heard of organic chemistry. Organic chemistry is the study of carbon-based chemistry because carbon is a sort of special snowflake because it has exactly 4 valence electrons. We'll go over why that's significant in a little bit. Okay, organic chemistry is the study of the chemistry of life. This is why carbon is so important. Okay, nitrogen over here, you are going to need to remember that it has 5 valence electrons. Okay, remember 1, 4, 5, and oxygen right here. You are going to need to know that it has 6 valence electrons. Okay, everything else you can always look up, and you'll get to know throughout the rest of the course. But it is imperative that you guys memorize these 4. There may or may not be a pop quiz in tomorrow's class. Okay. And so now we're going to go over something called the octet rule. So we've talked a lot about valence electrons because in biology that's pretty much all we care about is the outermost electrons because they dictate the characteristic of an atom, what it wants to do. So this octet rule, Octagon, right, stands for the number 8. Okay, the octet rule states that atoms will gain or lose electrons in order to have a full 8 valence electrons. This is what they want in life, okay? The only exceptions to this rule are over here, hydrogen, helium, okay, lithium, beryllium, and boron. Because you guys might remember from your reading and from the PowerPoint presentation that over here, helium, it has a full outer shell of just 2 valence electrons because the innermost shell, the shell closest to the nucleus, can only fit 2, okay? So hydrogen, helium, lithium, and beryllium, and boron all want 2 valence electrons. Every single other element, carbon, nitrogen, oxygen, fluorine, every single other element that we're going to talk about within AP Biology wants 8. Okay, that is the octet rule. So metals, if you'll remember from the PowerPoint that you were supposed to study yesterday, metals lose electrons to form what are known as cations. I've made this T a little plus sign so you remember that these cations are positively charged. Hopefully this rings bells from chemistry. Cations are positive. An example of this would be, let's take our friend potassium over here. Okay, potassium is a metal. And so potassium would want to lose its electron, right? Because it wants a full outer shell of 8. It currently has 1 extra, so it's going to kick it off. Over here, it's going to lose this little electron, and it's going to gain a positive charge. Why is it going to gain a positive charge? Because remember, potassium has a positive nucleus in its center, right? A positive nucleus because it has protons in this nucleus. And now that it's missing an electron because it's kicked it away, this electron is negatively charged. Remember, this electron is negatively charged. So when this electron leaves, the positive nucleus is now missing 1 electron to balance it out, to make it neutral. So this becomes an ion, and a positive ion, which is known as a cation, right? And nonmetals, so everything that is not part of group 1 and group 2 for the purposes, and including hydrogen. Hydrogen is not technically part of group 1. Okay, nonmetals tend to gain electrons to form anions. And remember, electrons are negative. So if something is gaining an electron, it is gaining a negative charge. Okay, in parentheses, when something is losing electrons, it is getting a positive charge. Okay, so normal ion charges for group 1 is going to be +1, for group 2 is going to be +2, for group 3 is going to be +3, and over here you see why carbon is so interesting, right? Because it has 4, which is exactly in the middle of 8. So carbon can actually gain or lose its electrons. It doesn't really care. It's very neutral, kind of like Switzerland, all right? And we're going to get into why that's really important in just a second. Nitrogen wants to gain 3 electrons, so it forms -3. Oxygen wants to gain 2 electrons to form 8, so it forms -2, because remember, getting 2 electrons means it's getting 2 negative charges, so -2. And fluorine, chlorine, bromine, iodine, so on and so forth, they want to gain 1 electron, only 1. Okay, they only need 1 to form 8 because they have 7. Okay, so ionic bonds, we're just going to briefly cover these. Ionic bonds form between a metal and a non-metal. And so these form by pure electron transfer. Remember, the metal, these two, want to give away their electrons. They just don't want anything to do with them. They're very, very reactive. And the non-metals over here want to gain electrons, right? So they're also very, very reactive. And as a result, there's this total transfer. It's kind of like, hey, I hate chocolate chip, you hate oatmeal raisin, let's switch cookies, okay? So it always happens between one metal and one non-metal, whereas covalent bonds are formed by electron sharing, okay? It's always formed between 2 non-metals. metals, all right? So for example, oxygen and hydrogen. Hydrogen is a nonmetal, even though it's over here. I know it's confusing, okay? Or chlorine and nitrogen, stuff like that, okay? So covalent bonds are formed between two nonmetals. So it's more just like, hey, we both like chocolate chips. I have 3 chocolate chips and you have 2 chocolate chips. Let's share, okay? Because then we'll be able to, between us, get 8 chocolate chips through strategic sharing. So the more electronegative element acquires most of the electron charge, all right? And you might be wondering, what is electronegativity? I kind of remember going over that in chemistry class. We're going to go over that in just a second. But first, ionic compounds consist of cations and anions that are arranged in repeating patterns. For example, table salt, NaCl. This is just your run-of-the-mill salty salt, okay? Table salt forms an ionic lattice. You might look at the table salts in the next time that you see it, okay? They're tiny, tiny little crystals. And that's because sodium and chlorine entirely ionize. They're not bonded together in a sense. They exist in this state, and they're attracted to one another because positive attracts negative, okay? So they don't exist as individual molecules. They're not really like, it's not like a molecule of NaCl. It's just an electrostatic attraction, okay? Whereas a covalent bond means that we have here hydrogen, right, has 1, it wants to get to 2, and it bumps into another hydrogen, right, which also has 1 and wants to get to 2. And they're like, holy cow, 1 plus 1 equals to what? 2. So if we share our electrons, we both get 2. We're stuck together till the end of time, but we both get 2. And that means we're happy together, right? So they form this sort of bond, okay? H2, this is a molecule, okay? This bond does not exist, okay? It does not exist in ionic compounds. That's an attraction because you see the charges here, whereas over here, we don't have any charges. We have a sharing of an electron pair, okay? Let's look at another example. Oxygen, a nonmetal, encounters another oxygen, a nonmetal. And oxygen's like, this oxygen's like, I have 6. And this oxygen's like, I have 6. And they're like, maybe if we strategically share a couple of our electrons, we can make 8. So if you look over here, if they share these 2 electrons and these 2 electrons between them, they each have 8 because the ones that are shared are counted towards both. So let's do some counting. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this oxygen is happy because it has 8. And let me change pen colors here. Okay. So this oxygen has 1, 2. Remember, these are both counted as both of theirs. 3, 4, 5, 6, 7, 8. Okay. So they form a double bond because they are sharing 2 pairs of electrons. So a total of 4 electrons. So each atom shares electrons with another in order to complete an octet. Okay, so just a brief review. Ionic compounds, there is a full giving or taking of electrons, which makes them form ions, hence the term ionic. Okay, they are made in formula units. These bonds form between metals and nonmetals. They have very high melting points. They are crystals at room temperature, and they are able to conduct electricity when molten or dissolved. Covalent bonds, on the other hand, okay, share electrons. They are not strong enough to fully give or take. They share, okay, hence the co in the covalent. Valent stands for valence electrons. Okay, they form molecules, discrete molecules. So for example, an O double bonded to an O, this is one oxygen molecule. They only form between 2 nonmetals. They have relatively low melting points, and as a result, Most are gases or liquids at room temperature. They are not usually solids at room temperature. Okay? So, for example, if we look over here at an array of sodium and chloride ions, you can see it forms this sort of crystal lattice, this crystal form. And that's the formula unit of table salt, sodium chloride. Okay? And its chemical formula is NaCl. Whereas over here, you see a collection of water molecules. Do you see over here, each individual water molecule is a discrete unit, whereas you don't have those discrete units within ionic compounds. Okay, so you get a collection of water molecules, and then you have a single molecule as opposed to a formula unit, and the chemical formula looks like this, H2O, because it's 2 hydrogens and 1 oxygen that forms the water that you and I drink every single day. Okay, so covalent bonding involves a sharing of electrons between atoms, but this sharing is not always equal. That is a really important point. And this point is why I have dragged you guys through an entire review of atoms and bonding, okay? Because water, back here, water is the basis of life. And what is biology? It is the study of living things, okay? Without water, there would be no life. And in order to understand water and its special properties, you really need to understand chemistry, bonding, polarity, and electronegativity. Okay, so let's go over polar covalent bonding. First, a review of electronegativity. Okay, remember, electronegativity is an atom's tendency to want to hog electrons. Okay, so I'm going to just fill in this table over here. Okay, so it increases as we go right on the periodic table, and it increases as we go from bottom to top of the periodic table. Noble gases do not have electronegativity values because they are complete. They have a complete outer shell. So obviously, do they want electrons? No, they're already complete, right? So if electronegativity is an atom's tendency to hog electrons, then obviously if you already have as many electrons as you want, you're not going to want any, okay? So fluorine over here has 7 valence electrons. Everything in this group right here has 7 valence electrons. So obviously, how many more does fluorine need in order to reach this beautiful number 8? It only needs 1 more. And so fluorine obviously is highly, highly, highly motivated to get that singular electron that it needs. Okay? Oxygen has 6 valence electrons. How many more does it need? It only needs 2 more. Okay? 2 more. Fluorine needs 1 more. Okay? It only needs 2 more valence electrons in order to complete its outer shell. So obviously, oxygen is pretty electronegative as well. It's going to hog electrons, okay? Nitrogen has 5 valence electrons, so it needs 3 more, okay? So you might see this sort of pattern. Fluorine is more electronegative than oxygen. Why? Because it is more electronegative than oxygen because it needs fewer electrons. So it's closer to its goal. So it's more motivated. Okay? Oxygen is more electronegative than nitrogen. Why? Because it needs fewer electrons than nitrogen in order to complete its valence shell. And so on and so forth. Nitrogen is more electronegative than carbon because carbon needs to either give away 4 or take in 4, doesn't really matter, okay? So carbon is not very electronegative at all. Does that make sense? Okay, and if we look over here at like lithium, for example, lithium either needs to give away 1, okay, give away 1, or it needs to take in, how many? 7, right, in order to complete its octet rule. So obviously it's going to want to give away. It's going to want to give away 1 electron. And so it's not going to want to get 7 because that's way too hard. So if it wants to give this electron, it obviously doesn't want to hog electrons. So lithium is not very electronegative. In fact, it's like the opposite of electronegative. Okay, hydrogen is kind of a special case because it can either give or it can take in order to be sort of complete. We'll talk more about that later. Okay, so an explanation of electronegativity. And I'm just going to read the slide because I wrote it. Okay, so imagine you're an atom. Your goal is to have a full valence shell, so either 2 or more often than not 8 electrons. Okay, you will do anything to get this full valence shell. However, depending on how close to or far away from 8 you are, you will have a tendency to want to give or take electrons. For example, if you only have 1 valence electron, it's easier to give 1 than to take 7. Electronegativity, this vocabulary word that is so important, is a measure of an individual atom's tendency to take electrons, okay, to take electrons. So the more electronegative an atom is, the more it has a tendency to steal another atom's electrons. So remember what I said about hydrogen, helium, lithium, beryllium, and boron? They are closer to being complete when they only have 2 electrons, not 8. For every other element, the octet rule holds. Okay? So polarity occurs when you have 2 atoms that are covalently bonded together, so 2 nonmetals sharing electrons to make a molecule that have different electronegativities. All right? So a nonpolar covalent bond occurs between 2 identical atoms. Since each atom in a nonpolar bond has the same electronegativity, the electrons are shared equally. All right, so for example, if these are both oxygen, okay, or actually, let's say, they're both oxygen or they're both hydrogen, for example, okay, hydrogen is probably actually more accurate because they're only sharing a single bond. If they're both hydrogen, they're going to share the electrons equally. Notice how this cloud of electron, okay, around it is equal size. They're going to share it equally because they both hog the electrons the same amount. Okay, 2 identical atoms are going to hog the electrons the same amount. So H2, N2, O2, F2, Cl2, Br2, I2, these are all nonpolar. And you can tell because they're all just 2 of the same atom bonded to itself. Okay? Think about it like a tug of war. If you have 2 kids that are the same size on either side of the same rope and pulling at the same strength, this rope ain't gonna move anywhere, right? However, that's not always the case. And that's when you get polar covalent bonds, okay, or more often referred to as a polar bond. This is a covalent bond, so 2 nonmetals, in which the electrons are shared unequally, okay? So the more electronegative atom, remember the more electronegative an atom is, the more it wants to hog electrons, okay? The more electronegative atom attracts electrons more and has a slightly negative charge. This is a lowercase delta, the Greek letter delta, okay? And so it develops this sort of partial negative charge, okay? And the other atom develops this sort of partial positive charge, all right? So over here, you can see this cloud is bulgier around, we can say this is an oxygen and this is a hydrogen, okay? Okay, so oxygen is more electronegative than hydrogen. Why? Because it is closer to 8 than hydrogen is, right? So hydrogen kind of wants to give away its electron. Oxygen really wants to get its electrons, okay? So it's going to form a polar covalent bond. And as a result, because the electrons are closer to oxygen than hydrogen within this bond, this is going to be more negative, right? Because they're closer to oxygen. Whereas because the electrons are further away from hydrogen, it's going to be a little more positive, okay, partially. It's still part of this bond. Hydrogen still has those electrons, but it's just going to be a little further away. So the nucleus, which is positive, is exposed a little bit more, so it develops this partial positive charge, okay? So imagine it kind of like the more electronegative atom has more juice on its side, and it's definitely going to hog the electrons more towards its side of the bond. And pull as the other one might, it can't pull very hard. So there's always going to be this sort of negative, partial negative charge over here, and a partial positive charge over here, okay? So this is what we call a dipole, okay? A bond or molecule with slightly charged ends, okay? It's called a dipole. For example, hydrochloric acid, hydrogen chloride, okay? The chlorine, which is more electronegative than the hydrogen, is going to have a partial negative charge. You notice this electron cloud over here where most of the electrons are spending its time, whereas the hydrogen is going to be partially positive because the electrons aren't spending as much time around hydrogen, okay? So the polar nature of a bond can also be shown by an arrow pointing to the more electronegative atom, kind of like what I drew with the tug of war, right? There's this little plus sign, so you can remember this is positive, okay? This is a plus sign, and then draw the arrow towards the more electronegative atom, okay? So I want you guys to take this time. This is also going to be in a Google Forms quiz, so take the time to identify the bonds between these elements as either ionic, polar covalent, or nonpolar covalent. All right? So I want you to, I guess you can't technically draw or place a partial negative symbol, but I will know by your responses on the Google form whether or not you can see the partial negative symbol above the atom of the polar covalent bond. Also, just for your edification, if the polar bonds in a molecule cancel out, the molecule is nonpolar. Okay, you see how this is parallel? It's nonpolar. Even though oxygen is more electronegative than carbon, this is a polar bond, this is a polar bond, but this entire molecule is nonpolar. Does everyone understand that? But when polar bonds do not cancel out, the molecule is polar, okay? So over here, we have our partial negative oxygen, and you notice how this isn't symmetrical, so the partial, it kind of has two ends, okay? So the hydrogens are both partially positive, and the oxygen is partially negative. And notice what molecule this is? That's right, it is H2O, also known as dihydrogen monoxide, also known as good old-fashioned water. And that's what we're going to be covering in tomorrow's lecture, and it's the biochemistry of water. Okay, thanks so much. I know this is really long. I appreciate you guys for bearing with me. This is a college level class, so you are going to be doing college level work, and I expect that you guys come to class prepared. See you guys tomorrow.